Hello, my name is Eva Muñoz. I'm a PhD student of the Université Libre de Brussels, and I would like to introduce today a part of the ModelFLOWs app, which is inside the deep learning framework for pattern detection, which is using autoencoders for pattern detection. So let's start with a motivation. Why we are using autoencoders? So we have seen in a previous article that autoencoders are really useful are also useful for pattern detection, as they were compared with another technique as DMD, POG, or VQPCA for the same purpose. So we are focusing on this part here, the autoencoders. For that, they were using, and we are going to use here, this database of modeling two-plan synthetic jets. What are two-plan synthetic jets? So they are devices. We have a membrane or piston here that force the fluid, like moving backward and forward, force the fluid to being expelled from the cavity now in an injection phase, and then re-entering it in a suction phase. So let us continue with the methodology of what are autoencoders and how we do it. So autoencoders are a deep neural network that provides unsupervised feature extraction. For that, we have to start with an input of P neurons, so it will have P dimensions, and we compress it during the encoder into a compressed data with M modes or M encoders. So that way we are compressing the information because M will be lower than P. And then during the decoder, we decompress the information to reconstruct the input. For that, we are going to use a database. The database has to be preferred in order to have the number of variables in the first, it will be a snapshot threshold that the first dimension will have to be the number of variables, for example, streamwise velocity. Then we have the spatial dimension, and finally the temporal dimensions. And the algorithm will compress it into a matrix that has this spatial dimensionality, which we have named to this, and the second dimension will be the temporal. In our case, the database will be displayed this way with two variables, streamwise velocity and span-wise velocity. Sorry, normal velocity. These are the spatial dimension, nx and ny, and we have around 4,000 temporal dimensionality. So the spatial dimensionality is around 200, and the temporal dimensionality is 2,000 and 4,000. This is only for matters of you understanding the dimension of our problem. And let me remark that we are going to compress the temporal dimensionality. So this part here, this P will be around 4,000 in this case. So how we're going to calibrate it? First of all, we have to design the seed, the number of test and training size. We recommend it, the test site is recommended to be at least 20%, so the training site lower than 80%. Then the number of modes, which has to be strictly lower than the number of training in order to obtain a compressed model. And we recommend it to be around 10. Then during the training, the coder will divide this site, the training site, into batches. So the recommendation is that the batches will be a power of 2, like 32, 64, and these two first values are really used in the industry, in the literature, because they give really good results. So we recommend one of two, both, and then the epoch number. The epoch number is the number of iterations that the algorithm does in order to achieve the solution. Just take into account that our algorithm also has implemented an early stopping. So if the number of batches is high, maybe the early stopping will stop when it's decided that the solution is converged. And finally, we're going to see here the result. These are the two most contributed autoencoders modes for in our dataset, and we can see that they are really similar to both the DMD and POD that are very useful for pattern detection in the literature, and they are already implemented in a lot of cases. And we can see that, for example, the first contributed DMD mode, which is associated with the frequency, its more important zone, the high intensity zone, is two lobulus in the inner of the jet. These are the exit of the jet. as we can also show them in the autoencoders. And the second contributing mode, which is really important in this case, which is like this, we can see this form of diagonal form in both of the autoencoders, as well as in the PUD. You can see more information in the link there. And in that case, we have also conveyed with a local PCA technique that you can see here more references about it. And that's all. Thank you for watching, and you can visit more videos, download the app, and a lot of more things in this link. Thank you.